less than that, I'll feel less than 4 G's of acceleration, okay? Or 4 G's of force, rather. Okay. Then we come down. Once I know that velocity right there, I come back to my work energy, or I go to my work energy, and I say T1 plus V1 plus work done from 1 to 2 is T plus equal to T2 plus V2. This thing is not the way I'm going to define my datum. I set my datum equal to 0 down at the bottom here. Right? And so I'm going to say there's no potential energy there. There is no friction force. There's no external force acting on this. So my work right there is 0. And the thing starting out at rest at the top there. And so that has no kinetic energy. So basically going from potential energy at 1 to kinetic energy at 2. So potential energy up here down to kinetic energy down at the bottom. So that's what I do. It's mgha is equal to 1/2 mv squared, v2 squared. Right? And then out of this, put in your numbers, out of this pops out what that height is, right? The height is 22.5 meters. I will say, lots of weird units going on in this problem and the other problem. People not realizing the difference between a mass and a weight, especially the next one. The next one, when we had English units, that's where people were really thrown off. Or using 32.2 for gravity in this problem, right? 9.81 for this one, because we're in those units. Okay, any questions about that one right there? That first part. Okay, so then we come down, now we've set that height, right? And then I guess too, like, well, which height is going to control the thing? You know, the point at B is not going to be affected by what's happening at C at all, right? It's not at all. Chronologically, it doesn't matter what's happening after that time. So that's what sets HA. HC, right? Not feeling any downward force over there we're gonna control how much downward force we have by setting that HC. Okay. So in this case, the key here, draw your free body diagram, mass times gravity going down. Your normal force is going to be 0. I have it drawn up here, but I said no normal force. So I mean, either way, it's 0, right? And so I set my normal force like that. I write my equation of motion. Mg is equal to mv squared over r. Mass is, by the way, good job knowing that you didn't need the mass. I thought I was going to get flooded. I mean, I don't know what the other half, if you guys flooded the MTS or not, because I wouldn't. By the way, free donuts on Friday. There's no way I'm going over there, right? There's no way I'm going to go over to that other room. I know you're getting screwed. I could maybe switch it. I'm a little worried. I think it would be about half and half. It would be split. Yeah, that's right. I don't know. But free donuts on Friday? I mean, like, I can't pass that up. I always have to be in this room. I don't want to do it. I know if I switched the rooms, it would be chaos. You'd think it wouldn't be. That's exactly right. You're college kids. I don't trust you. All right. I don't even know what you're talking about. What the fuck? Oh, yeah, good job not needing to know the mass. I thought people would ask that question, but throughout this whole thing, the mass cancels out, right? And so you don't need to know. So this answer applies to any mass of people that are up at the top. Okay. All right. So back to this. So then we solve, set the equation of motion, solve for the only unknown in this case, which is the velocity, which is 14 meters per second, right? And then I again go back to this. And now when they go over this top part right here, you can go from the energy state at A, or you can go to the energy state at B, because energy is conserved everywhere. And then you go to the energy at C. So I went all the way back to here, right? And I said, so kinetic energy plus potential energy plus work plus T2 plus V3. Because in this case, there will be kinetic energy and potential energy, the way that I've defined my datums, right? So my MGH1, which is the H1 is just the 22.5 that I had before, 1/2 mv3 squared plus MGH3. And that's what I'm after, is that H3. So then you plug in your values, 9.81 times 22.5 is equal to 1/2 14 squared. I use that velocity right there. And then plus 9.81 times HC. And then you solve for the unknown in there, which is HC, which should be around 12.5. Okay. Questions about that one? Well, where people mess up, like I said, 80%. It was pretty good on this one. Where people messed up was, like I said, the 3M, or coming in and calling this just the 4 mg, just this part right here, and leaving out this negative mg from gravity. which you would have caught had you drawn a free body diagram. That was one. Oh, flipping. There was a little bit of flipping, you know, at which point these ups and downs were happening. There was some messing up of which radius to use, right? It's 15 meters and 20 meters. Accidentally just transposing those things, doing the right problem, but having them backwards. Right. But for most part, it's pretty good. Questions about this one? Okay. Let me come down to this one. Right? This guy's a little collar in here. It's sliding along. It's slamming into this guy. I put a little Velcro in between. And the original problem that I got out of the book didn't have Velcro there. It just had them actually coefficient of restitution where they bounced off of each other. But in my case, I made it easier for you and added a little Velcro in there so they stick together. Then the two slide together and stretch the spring out. Okay. And so then what it asks us for is the initial velocity over here before the collision. Okay. There were several of you that came in and just said, this energy right here is going to be equal to the energy over here, and then left out the impulse momentum. And I told you I was going to do it, and I did it, and it was just zero. I was like, I'm not doing it. Like, I told you, this is the easy ones. I set it up. I do not do that. There's absolutely, energy is not conserved across the collision. Don't do it. Please don't do it. I said it. I told you. I said it. I did it. We did it. People did it. I did it. I backed myself up, right? Okay, so, right, there were some people all over here. One of the things people were kept doing, and I'm gonna take some of the blame here, but not much. We always had like friction or something that happened before, so we had to do like a state 1, a state 2, a state 3, and a state 4, right? We didn't need the first state over here because there's no energy lost going along. If it's a smooth rod, I didn't tell you how far back it started. I didn't tell you anything. So you could just work out the energy that this thing has just immediately before the collision. It's the same as the energy way over here, right? So you didn't need a step getting up to it. You could go right into it. And we did an example problem that had that. We had an initial step. This one didn't have an initial step. It basically just starts with the impact, okay? So the impact happens, and so we have conservation of linear momentum, right? Momentum is conserved across a collision. Energy is not conserved across a collision, right? So we just look at the momentum before is just mass times velocity. So mass A times the velocity, that's the only thing that's moving because B isn't moving at this location. It's equal to MA plus MB times V2. And so when they're stuck together, they have the same velocity. And so this equation right here assumes that, okay? So then, people got away with it here, right? Because a lot of people put in 1 pound and 11 pounds for the mass, right? You can get away with it here because technically the 32.2s cancel out, right? But you can't get away with it down here. This mass has to be in units of slugs. It cannot be in units of pounds. And if you do pounds, it doesn't work, right? And so a lot of people mess that up, okay? So up here, this is technically what it is. And really what it's saying is that V2 is just going to be 11 times V1, right? Or VA1. V2 is going to be 11 times what that is. Other way around. VA1 is going to be 11 times what V2 is. That's what I said the first time. You just misheard me. Okay. So then we set it up like this. Like I said, I like to do mine chronologically. I get stuck, right? I'm after this VA1, but I need V2 first, right? I need to know what's happening. And I'm going to get V2 from work energy down below, okay? All right, so then now I'm talking about the two that are stuck together. I need to figure out the velocity of them right after they got stuck together, and then they move to the right and they stretch out that spring, okay? And so what I do is I T the energy at 2 the kinetic energy at 2 plus the potential energy at 2 plus the work between 2 and 3 is equal to the kinetic energy plus the potential energy, right? This thing has no potential energy at the beginning. There is no change in height. There is no mass times gravity times height. Also, by the way, read right here. It says that the spring is unstretched. The spring is unstretched, right? So in this position right here, if a spring is unstretched, it is not storing energy, Okay, it's not storing energy if it's unstretched. So there is no potential energy in the spring. This was a big common, how people dealt with the spring was a common mistake throughout, right? They would say, well, the thing is, they would put 1/2 K3 squared right here, but that's not right because it's not stretched. There is no potential energy at state 2 because it's an unstretched position. Okay. Plus the work done between 2 and 3, there is none, right? Some people put in the spring there. You could do it if you do it right, but a lot of people did it and did it wrong, right? And one thing that was pretty common is they would put in work done by the spring right here, and then they would add also spring in the potential energy over here, and that means you're double counting the spring. You can't do that, right? So anyways, it goes all kinetic energy to all potential energy. Kinetic energy of the two moving to potential energy is stored in the spring. So we got 1/2 MA plus MB times V2 squared is equal to 1/2 KS3 squared. And then this is another place that people messed up, right? Is they came through and they said, oh yeah, this is a 3, 4, 5 triangle, right? That's 3, that's 4, and then that would make this 5. You could use your other trig to figure that out, but this thing is 5. Now is 5 the stretch? No, 5 is the length, right? The stretch would be 5 minus 3, right? Because I know the unstretched length. The problem statement told me that thing is in its unstretched position when it's vertical like that. So then the stretch would just be 2, okay? And a lot of people put in 5 there. A lot of people put in 4. 4 is also not the stretch. 4 is how far it moved in that direction. Some people went in and figured out, they were like, oh, the spring, I'm going to figure out the amount of spring that's just going in the X direction because that's the part that's going to affect it. That's not how this work energy works. It just matters about how much the spring stretches, which is beautiful about it. It doesn't matter with the angles of it or anything. It just matters that it's stretched. And then that energy went somewhere and it went into that stretching spring. It doesn't matter how much went into that direction or how much went into that direction. It's just how much it stretched total. Okay, and that's where the energy went. It's beautiful because you don't have to track all the angles and stuff like that as you go along. Okay. What was that? Okay, so yeah. So put a 2 in there. So this is 1/2 11 over 32.2. Again, you get the wrong answer if you just do 11 right there because the 32.2 doesn't cancel out on the other side, and so it absolutely matters that thing goes in sludge. Your units won't work out. Right, and then 1/2 KS squared is what that is. And so what you get is the velocity at 2. So the two of these things right after the collision have to be going 15.3 meters per second in order for this thing to move over to the right 4, which would stretch this thing out 2 feet. Okay. Did I say meters per second? Oh shit! Look at me, I'm fucking up my units. I was like, you guys' units are all over the place. There's my units all over the place. But I'm a doctor. I get to do it. I'm leading the show, so I get to do whatever I want. I can switch to meters right there if I want. Okay? So then you take that 15.3 feet per second, put it back in, and then solve for this. Basically, it's going to be this number times 11 is what it'll end up being, right? And so at 168.33 feet per second is that velocity. So it's going to come in at 168.33 feet per second, and it's going to slam into it. The two slow down because there's 2 of them. You got a 1 pound thing slamming into a 10 pound thing. And so it slows down to 15.3 feet per second. Okay. And this, right? The energy lost, you just look at the energy before the collision and the energy after the collision, right? The energy before the collision is energy before the collision is this, right? Oh, we don't have it there, but it is, just 1/2 mv squared, right? That's the energy before the collision. And then the energy after the collision, I went with velocity minus 1/2 mv squared, right? You could also do 1/2 ks3 squared, either one, right? Because they're equal to each other, right? That we just read up here, we said we figured this velocity so that these two were equal to each other because the energy is conserved after the collision. And so when you calculate that out, you get 400 pound-feet or foot-pounds. You do not get joules. You do not get joules. You do not get joules. I'd say an overwhelming majority said joules. And I said in class, didn't remember that? I said You don't get joules because everybody does this every year. They put the energy in joules. Joules is a metric. Is an SI unit. You don't get joules. You don't. Do you remember when I said this? I said, and then I go, I don't know what the other equivalent is besides foot-pounds. And then remember this, and then so it was like horsepower, but then that's more. That's work. Yeah, that's work over time. That's work over time. But so we don't know. But I do know in this case it's foot-pounds and it's not joules. You guys look at me. I said it. I know I said it. Does anybody remember me saying it? Thank you.
It was on my grade sheet too.
Yeah. Okay. Did you write joules though?
No, I put.
Oh, hells yeah, bro.
Forgot
Yeah. Hells yeah. You forgot what?
I forgot to divide by 32, so it doesn't matter.
Okay. Dude, no, only one person remembers me saying that. I said it's not joules. You motherfuckers. I said, because I was a hint. It was a hint into the future. Because I know that this happens every time. And I was like, listen, when I say it, it's not this.
Write it on the exam next time.
Yeah. I also, by the way, I put a little note at the bottom. I know that people are going to mess up units on pounds and masses. And that's why I put a little note. If you look at the top of the exam, the little note that says, hey, in English units or imperial units, mass is not pounds. I said that, and I tried to help you. Okay. So mostly the big problem there was the springs. Energy being conserved across them and then the springs. Okay. So then the next one was how much force is exerted between the two. And there's a couple ways you could get there, right? Basically, you got to go back. This is on the practice exam too. Force times time causes a change in linear momentum. And so you could look at how does the force over time change the momentum of the 10-pound block, right? And so that's what this one is, 10-pound block. So that would be 23.56 because 10 goes from 0 to 15.3. So I could figure out what kind of force would be required to do that. Or you could look at it in terms of what does B do to A? Well, B do to A would cause it to go from 168.33 meters or feet per second to 15.3 feet per second. And so then either way, you should get that those things are equal and opposite to each other. And so the answer there is 2375.78. Yeah. Right. And also, by the way, there's several times, you might go in there and be like, well, I got answers really close to this. So then, because again, give me some regrade requests if you want. But you might be like, oh my God, my answer was really close to this answer, or my answer was really close to this answer. You should give me credit for this. But the problem is how you got there. It may have just been an accident. Okay, you may have gotten lucky and you made mistakes on both sides or several different places. And sure, your answer looks the same, but you got there in a really strange and illogical way. But that's what I'm leaving on you. You go find it, because if I guarantee I've made mistakes as I've gone through. I've missed something. I haven't interpreted something right the right way. Find those things and learn from it, and then you come to me, right? And do it in a professional, non-aggressive, attacking manner if you could, okay? If you could do that. I know you might be mad. Maybe just cool off first and then write the email. It's a common thing to do as you move forward. It helps a lot. Just cool off first before. I've been saved by that many, many a times of like getting an email and then I respond to that email and then I just say, you know what, I'm not gonna send this, I'm gonna wait, and then tomorrow I'll send it, and I cool down and I'm like, thank God I didn't send that, right? And sometimes it's like, I wish I would have said it when I was pissed, right? Let's do this. Okay, but don't do that to me, don't attack me. Okay, any questions about that? And the next exam is in fact in not this Friday, not the next Friday, but the following Friday. I think it's November 1st-ish. Yeah, the day after Halloween. Is that true? Yeah. Yeah, that's awesome. You guys didn't want to go out on Halloween anyway, right? Well, it was an accident. I'm not a college kid. I don't remember that anymore. Yeah. Were you gonna go do something cool? Were you gonna go?
Not anymore.
Yeah. You were, but then you're like, oh shit. And all your business major roommates will be all just out just having a blast. I do have a joke. I have a joke for you. I mean, if I told you this joke, you don't know what it is yet. So, okay. So we call ourselves engineers. Have I talked about this? Okay, so we call ourselves engineers at this point, right? But you actually haven't graduated, right? But you still call yourself an engineer. You don't hear like pre-med students going around calling themselves doctors, and you don't hear art majors going around calling themselves unemployed, right? So, yeah. Tell that to one of your art major friends. Right? If they're out partying and having a good time, and you're on Halloween, you'll be studying for your exam. You know what I'd be open to? No, this next Friday. Okay, well, you've done it to yourself. It could be next Friday.
Do the review session on Halloween and bring us all candy.
A review session on Halloween, that'd be
Yeah,
right.
you gotta dress up in costume.
Yeah, I do that.
The best costume gets 100%.
What's on the next one? 2 points extra credit for costume.
So we won't be far enough by next week. Okay, yeah, we don't want to do that. Because it'll be, one of the questions will be the stuff that you're doing right now, the kinematics of 2D rigid bodies. Well, that's one of the problems. And the other one is going to be kinetics of rigid bodies, which we have not done. That's what we're going to be covering today, or starting today.
There's one question.
2 questions.
No, but we can just.
Oh, just do 1 question. No. All or nothing. Do half of it this Friday and half of it the day after Halloween. Because when is your mechanics materials exams? Like, when are those?
The same as
Same week.
Oh, same week, but not the same.
Same week, but on Wednesday.
But on Wednesday. See, I set mine first, and I was like, hey, don't put them on these weeks. And then he's like, fuck those guys. I'm gonna put it on those. He's like, I'm gonna put it on those weeks. You could do it the Monday. I'd be down with the Monday. Why not the Monday? What? Oh, it is. Yeah, you don't want that. That's worse than Halloween. So this is a book that I read / had someone read to me. A short history of nearly beautiful. I really highly recommend it because it just goes back to like way back when we first started discovering stuff and how we discovered atoms and things like that. And well, it's a short history on nearly everything. It's pretty cool. How we knew that Earth is as old as it is, and when we discovered that, and like what methods we use. It's pretty cool. At least, as a nerd, I really enjoyed it. Okay, mass moment of inertia. So before we get into, because what we're doing here, kinetics now. Kinetics is how forces relate to motion, right? Right now, all we've talked about is things moving, right? We got rigid bodies and gears and things like that. But how do we figure out the torque that needs to be applied to give us the alpha that we have on here? How do we figure out what kind of reaction forces those things turning are going to do, right? So that's where kinetics comes in. We need to relate forces to motion. In 1D stuff, it was just F equals ma, right? F equals ma in the x and y direction. That was our equation of motion. Same thing's going to apply here. We're going to have F equals ma because that's still happening. But then we also have to relate moments to something, okay? And those moments are going to be equal to some other equation. It's not F equals ma. It's going to be I times alpha is what it's eventually going to be. And what I use is going to be, so moment of inertia. So it's going to be dependent on the moment of inertia. So we have to take a little side step before we get into that and talk about moments of inertia. Now, these are different than the moment of inertias that you're learning about right now in mechanics materials. Are you learning about that in mechanics materials right now? Yeah, so these are different. Just to add confusion to it, they call them the exact same thing. This was called a mass moment of inertia, and what you're learning there is an area moment of inertia. And they have very similar meanings, but they have different units, okay? The mass moment of inertia is what we're talking about today. That is well, how about we write some notes down? It is a measure measure of how a mass is distributed about an axis. Right? And what the area moment of inertia is how an area is distributed about an axis. Right? That's what you're learning in mechanics. This is how a mass is distributed about an axis. Okay? This is a measure of a body's resistance to rotation. Similar to how mass is a body's measure of resistance to translation. Okay. And then we add one more note. I'll explain each of these things. Not, I said this before, the same as area moment of inertia, which is resistance bending. Okay. The area moment of inertia is an object's body's resistance to bending, right? If you have a big moment of inertia and you try to bend it, it'll be harder to bend something with a big moment of inertia than for something with a small moment of inertia, okay? And it differs depending on the axis, right? If you bend something about its weak axis, it's really easy. You flip, like you take an I-beam and you put it on its side, it's easier to bend that way because it's moment of inertia that direction. It's more concentrated around that axis. It's easier to bend. You flip it up, then you try to bend it when the area is distributed more. It has bigger moment arms, and so it's harder to bend it. Similar thing's going to be happening here, but this isn't bending. This is rotation. A perfect example of this is a pen or a pencil. I don't like how low that is. That's right, I'll leave it. Motherfucker. I don't know, it's bothering me. No, this is out of the way. I was gonna fix it. Okay, take your pencil, right? And then you're gonna actually have 3 axes of rotation on your pencil, right? And so if I just try to take my pencil and you try to just translate it, don't rotate, just translate it. Like you can feel it, right? You can feel it in your hand. Picture a shot put. I got a shot put in my hand, right? And I'm gonna throw it. Like when I go to throw it, I feel that resistance, right? If I go to, just imagine your head, I can feel it, right? What you're feeling is that mass. And the reason you feel it, the harder you try to throw it, the more it's almost pushing back on you, right? That's fictitious inertial force, but you can feel that mass, something that's more massive. You feel it even more when you try to accelerate. So what you're feeling there is the mass. Now picture your pencil here, and if you try to rotate it up and down, you can feel there's a resistance to that. If I hold it in the middle, there's less resistance, right? Because it's like what we're looking at is how much is that mass distributed. In this case, this direction, right? It's distributed on either side, right? And it's like, oh, it's distributed pretty good, and I can feel that. It has resistance to it. I can't rotate it. That what you're feeling is its moment of inertia. But then if I grab it on the end of it, right, you feel it even more, right? You feel it even more because now it's distributed even more. Here's my axis of rotation over here, but the thing's really long. That mass is really distributed out, and it's harder to rotate it, right? And you can feel that rotation. But then what about if I rotate it around this axis? Right? Do you think there's going to be much resistance around that axis? No, because the whole thing is really concentrated around there. Your mass is not distributed. It's really local along that axis. So if I try to rotate it, it's hard to feel. I need to get something bigger so you could really just start throwing rods around in here. But you can feel that doesn't have much resistance. So there's a small moment of inertia around this axis, and then there'd be one coming up this way in the middle, and it's a bigger moment of inertia. And then there's actually one going this way too, that direction as well. And it has a moment of inertia, which would be the same as the one going this way. It would be the same this way. But we'll calculate those in a second. But that's the moment of inertia. It's that resistance to rotation. And where you grab your object by, it's going to affect your moment of inertia, right? Like grab my pencil by the... Throw it around too much. Yeah. Just trying to get it. Yeah, trying to get it, yeah. And so if you grab your pencil by the end, it should have a different moment of inertia than if you grab it in the middle, okay? So That's it. That's your motivation there. So that's the moment of inertia. So clearly we need to take this into consideration with our calculations, right? If I'm trying to accelerate my pencil from grabbing it on the end, I'm trying to accelerate it up like that, the moment that I need to apply to make that go up is going to be bigger than the moment that I would have to apply if I grabbed it from here. Or it'd be bigger than the moment to get it than I would need to get around this rotation. So somewhere we have to incorporate the moment of inertia. So we will do that eventually. But first, let's talk about how to calculate. So these are how you calculate the center of mass. This is very similar to how you calculate the center of area, the centroid, right? It's a weighted average. So if you go through and you break your object up into little components, it's just a weighted average. It's the distance for the distance between the center of this thing times the distance to the center of this mass, and then divided by the total mass. We'll do some examples. You can see it a little bit later, but this is if you break it up into little sections. This is how would you calculate that, and even just individual elements, how you calculate the center of mass, right? So then the mass moment of inertia. Here's the equation that we're going to use for that, right? And we're going to call it IO. That's going to be the integral of r squared dm. Right? I'm just telling you that. That's what we're going to start with. So what it is, we have a little dm, and we're trying to calculate the moment of inertia about an axis. So this is the axis right here, and then this LO, and then he's got this big blob, and then there's this little differential mass in there that we're going to have to integrate. And the distance between the axis, this axis, and the center of this dm, this is what r is. Right? Is that distance, right? And so so we've just defined it as being r squared dm, and then you can imagine there's just these little dm's all over the place, right? And so then this integral would take into consideration all of those things, okay? And so r is the perpendicular distance. Just to finish these out. I don't know how to spell perpendicular. Yes, I do, because my we'll do some examples here in a second. That is the pure definition of what the mass moment inertia is. Oh. Right. Units. It's going to be a mass. Oh. Mass times distance squared. Right. They're all going to be mass times distance squared. So a kilogram times meter squared, right? Beautiful. Slug. God, I hate slugs. A slug or a slinch. We talk about slinches. A slinch is when you're talking about masses in terms of inches per second squared, right? It's called a slinch. A slinch per times inch squared. Anyways, there's a distance times that. So that's not what are your units on mass moment of inertia? Yeah, distance to the fourth. Distance to the fourths, right? And so these are not those. These are not those. Units are not the same. But the methods you learn, like you've gotten into parallel axis theorem, and yeah, same deal. Oh, you did that with statics too, right? You did statics? Yeah. Same concept, same principle, just different units. You were just dealing with masses instead of areas, right? So that's why it's not too difficult for you. I think it's an easy subject. You guys hate it. You guys hate moments of inertia? They're kind of tedious and stuff, yeah. And not necessarily that you hate it, but you're terrible at it. Okay. Let's just do a quick little example. What's beautiful about these, and there's a little foreshadowing, is you don't calculate this stuff very often. You don't actually carry out the integral because the book has already done this for a bunch of standard shapes. But I just want to show this applied to an actual object. So here's my pencil. This is a slender rod, okay? The slender rod. The throughout this text, we make an assumption when you see this slender part, what it's saying is just it's really thin. It's really thin to how long it is. And because of that, what do you think we call Ix in this case? The moment of inertia about X. We call it 0, right? Is it 0? No, it's not 0. Okay, but we call it 0. we call it 0. That's that's why they're calling it a slender rod. It's just saying that it has no resistance to rotation about this axis that goes through this x-axis. Now, I guess the other thing I wanted to mention, when you see these primes floating around, this is like the whole, like, like the brotherhood of mechanists. When you see the primes, right, they denote the center of mass. Denote center of mass. So when you see those, because what we're going to calculate is the moment of inertia about the center of mass. The center of mass is right here. So when you see the primes, that's what it means. Because that's some later on cases, we're going to want the moment of inertia about the end, right? This is like when we held our pencil from the end of it. Those would be Ix, Iy, and Iz, but not primes. The primes say about the center of mass, okay? And so just be wary of that and just start getting that in your head that that's what we mean by that. Okay, so they're calculating Iy prime. Let's figure out what the moment of inertia is about this. And so we'll go back to this original definition. Iy prime is equal to the integral of r squared dm. Hard to carry out that integral in this form, so we're going to change it around a little bit. Some of these variables. We're going to define dm, a differential mass, right, is going to be equal to the density of the object, rho, times the cross-sectional area of the object, times dr. Right? Rho is the density, so if I take rho, the density, and I multiply it by a volume, it'll give me a mass, right? Density times volume gives me mass. My volume is cross-sectional area times a differential length, right? So this is going to be cross-section area just to show you how we get there, that this is, right, differential length, right, and this is density of the material. Right. Okay, I'm going to take that and put it into this equation over here. Iy prime is equal to the integral of r squared times rho times a times dr. So now I've turned it into an integral. Instead of integrating over dm, I'm integrating over dr, which is the length of it, which I could do in this case, right? Because I know, right, I can integrate over that length right there. And so for this one, right, my center is right here. And so my length that I'm going to be integrating over, if this is L, is going to be from negative L over 2 over here to L over 2, right? Negative L over 2 to L over 2. So when I do this integral right here, this would be negative L over 2. This is L over 2, right? And if I carry out that integral with that definite integral, what I get here is rho a L cubed all over 12. So if I just carried out that integral, that's what I would get. My total mass, just a little side note, my total mass would be rho a L. Right? If I take my density and multiply it by the cross-sectional area, multiply it by the total length, it would give me my overall mass. So I'm going to take that and put it back up into this equation. All right? This would be Iy prime is equal to ml squared all over 12. Okay? That's what we get for the moment of inertia of a slender rod about its y-axis. ML squared. Very familiar, right? Like I said, it's going to be confusing as hell if you're first learning this stuff, because what is it? What's the equation you use for like a rectangle? The moment of inertia, area moment of inertia? Yeah, it's BH cubed over 12, right? BH cubed over 12. Well, shit, this is very similar to that, right? This is ML squared over 12, right? So then, right, there's your mass and there's your distance squared right there. So that's the Iy prime. How do you think this relates to Iz prime? Same, right? Either I'm rotating this way or I'm rotating this way, right? So it's the same. So you could say that this is the Iz prime. Same thing. You get the same answer there. Now, if I was to change this and say, okay, what is the moment of inertia of this guy about its end? What would I do different if I wanted to feel the moment of inertia of this guy about its end?
Integral bounds.
Yeah, these guys, right? Instead of negative L over 2 to L over 2, you do 0 to L. So say we'll call that IY is equal to the integral of from 0 to L of rho, or r squared rho a dr. Then what you get there would be ml squared all over 3. Right, and note there, I left the prime off of it, right? So this is about its end. Right? And like I said, it should be bigger, right? Because it has more resistance to rotation at the end, right? And it should. It's 4 times. Did that math in my head. Pretty proud of myself. It's 4 times the moment of inertia on the end. Okay, so this is the good news is, right? Like that was kind of a pain in the ass because we had to do an integral. We always hate doing integrals, right? But good news is we don't have to do it, right? This has been done for us for a bunch of standard shapes, just like you did in mechanics of materials. So here's our slender rod, right? So this comes directly out of the text. By the way, open the text sometimes, right? Like you could read it. Like if you're struggling a little bit, open it up and read, right? That's one thing I learned after nearly 10 years of going to college. Right around year 8, I was like, holy shit, this is what he just was talking about. Look at this. And it's saying it a different way and maybe a more complete way. And then he's got better drawings. And it's wonderful. Yeah, take a look. But this comes out of the text, one of the appendices, right? And so here, again, the primes here, right? See the primes. Those are the center masses, right? And they got it drawn through the center masses. And so that'd be these guys, right? This is what we just solved. Ix prime axis is 0, right? They assume that it's 0 around that axis. Iy prime is equal to Iz prime is equal to 1/12 ml squared. Then they have another set over here that's about its end, right? Same thing. Ix axis is going to be 0. Iy axis equals Iz axis is 1/3 ml squared. Right? Just what we count. Okay, so that's a slender rod. You also have another object that we're going to use in here quite a bit are discs, right? If you have a disc and you can figure out what the center of masses are, right down the middle, and you can figure out the moments of inertia of this thing about its axis. So there's the x-axis and the y-axis. The resistance around this guy or that guy is the same, which is 1/4 mr squared. But about the z prime axis, now that's rotating this way around the z prime axis, is going to be different, right? It's going to be different than that. All right, and so just be really careful. People know where to go find these things, but then they kind of read them incorrectly. Same thing here. Again, the y primes is through the center, and then they also give you the moments of inertia about the bottom corner, right? And so that's going to have larger moments of inertia than about its center of mass, and so then they give you the equations for that, right? And then there's different volumes and stuff like that they could deal with as well. When we get into 3D, these guys will come back and we'll have to look at these a little more because we're all just doing 2D stuff right now. But really, there's going to be all 3 different axes. Yeah.
Are these going to be things we're given on the exam?
Yes, absolutely. I need you to write down on your equation sheet, draw pictures, and then nope, I'll give this to you, Mark. Okay. All right. But then oftentimes, right, these are beautiful, that's great. They've done these for us. But what happens if you don't just have a slender rod or you don't just have a perfect rectangle? Well, what do you got to do? Well, we got to use the parallel axis theorem. We have to break it up into a bunch of smaller things, possibly a rod attached to a big disc. And then we have to work out what the moment of inertia is of the whole thing attached together, or the whole contraption attached together. So then this is where we'll take off next time is the parallel axis theorem. It applies to this as well, right? Same methodology. And we'll do an example with that, and then we'll go on to F equals MA stuff. Cool. Break. Good job. Send me those regrade requests in a professional manner.
I hate you.
Yeah, I know, right? Some of them were like that. Yeah.
Hey Barry, can I get a signature for
What for?
a little midterm thing report?
Okay. This is
I agreed from a little bit ago, so
okay.
I was supposed to sign it last week.
Okay. I mean, what am I signing? Are you doing good? Are you doing good?
It's good. This is not good.
Okay. No.
It should be better though.
Get it up. Get it up. I mean, that works. It works. 67's the pass. Hey,
Thank you.
what is this for? This is rugby stuff? Is that what this is?
This is like just for a little scholarship.
Okay. Sure.
My Native American scholarship.
Yep. Yeah.
So that roller coaster on the exam.
Yeah.